Okay, so hi everyone. Today we will be going on our topic, which is Introduction to Summability Theory. Yesterday we stopped before a problem that is asking us how and in what way we can arrive at the concept of summability method. So a natural question can be stated as follows. Let D be a non-empty subset of omega, which is the set of all sequences. Can we find a rule which gives each sequence in D a generalized limit in real numbers? In other words, we are looking for a map from D into real numbers, like usual concept of limit of a convergence sequence. Okay. That's why we call it a generalized limit, because we expect it to be different than usual concept of limits. Okay, so to be able to do this, we will start with having two subsets of two subspace of all sequences. Let D and E be subspaces of all sequences, and the map phi be defined from D into E, a linear operator. Then we consider a subset of the set of D which consists of sequences from D such that the image of those sequences under phi should be included in the space of all convergent sequences. We consider this set, and now we can define the new notion of a generalized limit as follows. And the phi limit, the phi limit of x is defined to be as the limit of phi of x. So since we take this sequence x from CD, we can definitely talk about the image of x under phi. So phi of x is in C, which is the space of all convergence sequences. So we can consider, it makes to define phi of x as the limit of phi of x. So sorry, this is gonna be different. This should be different. The limit of f phi limit. This is our main definition here. So from this definition, we can say that we base our new concept of generalized convergence on ordinary convergence of sequences. So I'm gonna let you know a concept which is regularity of a summability method that we will need in the coming segment of our talks. Okay, a summability method phi is called regular provided that C is included by D and the image of C should be included in C, imply the phi limit of x equals limit of x with usual sense for all x in C. So if we go back the initial definition here, we say that we define phi limit of x as the limit of phi of x. But we know that the regularity says that if we take x from the set of all convergent sequences, then limit of x should be a finite number, right? Limit of x. I mean, the usual limit, the ordinary limit of x should finitely exist. But within this definition, we can't make sure that the limit of x equals to the limit of to phi limit of x. So regularity says that if each convergent sequences has a limit of has a phi limit as its own ordinary limit, then we call this method as to be regular. For now, so far I have not defined a formal definition of a summability method, but we will arrive at it. It takes some initial examples to make it look more understandable. So we will arrive at later. So I'm gonna give some initial examples. Okay. First one is pretty basic. Zero map. So let D be the space of all sequences, and the map V be from omega into space of all convergent sequences, and we define V of x as the zero sequence. So this map gives us more generalized notion of convergence. Why? Because we know that infinitely many sequences from omega does not have ordinary limit. There are some sequences which are divergent. But this basic example assigns every sequence to a limit which is the zero sequence. So now we are gonna define the new limit of this concept as that way. So the V limit of x is 0 sorry. So for example, even though the series of minus ones and 1 is not summable, its sequence of partial sums which is one zero one zero 10 and so on, is V summable to 0, since V limit of x is limit of Vx, which is 0 with ordinary sense. Another initial example comes from arithmetic mean of sequences. Using arithmetic mean, we obtain a further notion of a limit let D be omega and cap C1 defined from omega into itself. We define cap C1 as to be this equality sorry. So the subset that we are interested in is C cap C1 consists of sequences that is convergent under C1. So we can talk about this definition for any sequence from omega, right? We just take the arithmetic mean of the terms of x by this definition. So we can always think of image of any sequence under this map, but we are interested more in the ones who goes into directly in the space of all convergent sequences. So we underline this subset by that way. We are interested in these subsets of omega. Okay. Then for each x from C cap C1, a generalized limit is defined by C1 limit from C cap C1 into real numbers. C1 limit of x is defined to be limit of C1x. So this is well defined because we make sure that x goes into convergent sequences under C1. So C1 of x has a limit with usual sense, ordinary sense. So C1 limit of x can be defined as the limit of C1x. So one may easily check that the sequence of 1 0 1 0 1 0 is in C caps C1. I mean, even though it is so obvious that this sequence is not a convergent sequence, it is clear that we can assign it a limit by this method, because it is pretty straightforward to confirm that the C1 limit of y equals 1 over 2. And another example comes from the sequence x 1 0 minus 1 1 0 minus 1 and so on. This is not a convergent sequence, it is obvious, but it's in C cap C1 since C1 limit of x equals 0. Yeah. So I'm gonna give you another example as a generalized notion of limit. Now let d be omega again and map z 1 over 2 be defined as follows. X n minus 1 plus xn over 2. So C cap z 1 over 2 consists of sequences from omega such that z 1 over 2 of x in the space of all convergent sequences. Then then we obtain a generalized limit for every x from C z 1/2 by setting the z 1/2 limit of x is defined to be limit z 1/2 x with usual sense, with ordinary sense. So it is clear that the set of all convergence sequences, which is C, is included by C z 1/2 and z 1/2 limit of x equals limit z 1/2 of x for all x from convergent sequences. We can refer to the same sequences that I shared before as an example of this method. Also, the sequence of 1 0 1 0 is in C z 1/2 and z 1/2 limit of x is limit z 1/2 x equals 1/2. So we see that this method cap z 1/2 assigns limits to some sequences which are not convergent with ordinary sense. I mean, it is so clear that this sequence itself is not convergent, but under this method it can be assigned a limit with a more generalized method. So now I'm gonna prove a theorem about the method C1, which is called Cauchy's limit theorem. This theorem says that C is included by C cap C1 and limit, and C1 limit of x equals limit of x for all x from C. So as you can see in this theorem, we are trying to think of a result which can be considered to be equivalent to this result. See, in this example, we said that it is clear that C is included by C Z1 over 2. It doesn't need to be proved under a theorem or proposition, because it is so clear that this x n minus 1 can be considered as a subsequence of xn. Right? We know that xn is in convergence sequences. So then every subsequence of xn should be convergent. So if we sum two convergent sequences, we will have a convergent sequence, and we divide it by a scalar which is 2 here. We will obtain convergent sequences, and since xn minus 1 and xn has the same limit with ordinary sense, if we divide it by 2, we will obtain the same limit as xn's. So this part and this second part is pretty clear for this method. But when it comes to cap C1, which is actually Cesaro method, we need to do more to prove this. So firstly, we note that C1 is a sequence space because the operator from omega into omega, which is Cesaro map cap C1, is a linear operator. Okay. Then we make sure that C cap C1 is a sequence space. And moreover, clearly we have C1 of E equals E, which is the unit vector of all sequences, which consists of just ones. We talked about it yesterday, and we also said that C, the space of all convergent sequences is direct sum of C naught and the span of E. Because of these two facts, it is enough to show that holds, it is sufficient to show that C naught is included by C cap C1 and C1 limit of x equals 0 for each null sequence to prove the assertions given in the theorem. Okay. So let X be any null sequence and let Tn be defined as this. We need to show that this sequence, which is in fact the arithmetic mean of the terms of the sequence of X in C naught. Let any positive epsilon be given arbitrarily. Then we can pick a natural number k naught with xk is less than epsilon over 2 for all k greater or equal to k0. We can do that because we know that X is a null sequence, so thanks to well-known definition of ordinary convergence, for each epsilon we can find a fixed number of k naught which is dependent on epsilon, such that for all k's greater or equal to k naught we have this inequality. This comes from the definition of convergence of X. And also we also choose n0 from n such that k naught less than n naught and 1 over n naught plus 1 times k runs from 0 to k naught less than epsilon over 2 hold. So as I said, the first part, I mean finding, determining the number k naught, comes from the convergence of X, which is a null sequence. But for each epsilon we can also find a number of n naught which is greater than k0, such that this number less than epsilon over 2. It is clear that we can find such numbers for each epsilon. I mean, we have this k naught and we have this n naught. These two numbers are crucial in the core of this proof. This yields that for all natural numbers greater or equal than n0, the following inequalities hold. The absolute value of Tn less than or equal to 1 over n minus n plus 1 times plus xk. So we took n Tn as this, so we split it into two sub finite summation here, k runs from 0 to n, and we divide it into two summation that k runs from 0 to k0, and then k0 plus 1 to n. So we can write this inequality. So this inequality, this number is less than or equal to 1 over n naught plus 1 times plus 1 k naught to n absolute value of xk, and this number is less than or equal to 1 over n naught plus 1 times xk plus epsilon over 2, and this is also less than or equal to 1 over n naught plus 1 times the summation k runs from 0 to k naught of absolute value of xk plus n minus k naught over n epsilon 2. So we know that this number is less than epsilon over 2 from this. So this number is also less than or equal to 1. So we get epsilon over 2 plus epsilon over 2, which is epsilon. So we showed that for each positive epsilon, we can find a fixed number and 0 such that the absolute value of Tn is less than epsilon. That means that Tn is a null sequence. Thus, limit Tn is 0 and Tn in C naught. Okay. Okay, if you want, we can take a break a little bit. After we can go on, if it's fine with you. Okay, thanks.